So welcome to this video series that I'm doing on writing a DPD simulation in C. And this is a computer simulation, framework or methodology that's very useful for simulating polymers in a variety of situations, right? Whether you're talking about polymer solutions, polymer melts, we've used it for nanoparticles, things like that. And I thought we would just go through how to write one from scratch in C. And coincidentally, this month is the 30th anniversary of me learning to program in BASIC. And so I thought, oh, what a nice way to kind of combine everything together. So before we get started, though, I thought I would go over some caveats and disclaimers about this video. And the first of which is that I'm a polymer physicist and I'm not a computer scientist. And so what I mean by that is I've written numerous computer simulations for polymer physics. And the thing about it is I write fast code, it's high performance code, and it's correct. But for somebody who studies computer science and knows, really the nitty gritty of how these things are done, it could be that there are more efficient ways to do what I'm doing. And so I'm not saying that what I'm doing is the only way to do this, but it works, right? And so if you have a different understanding or a little bit more in-depth understanding of how you might do this, then absolutely feel free to take advantage of whatever optimizations you can make so that you get an even faster code than what I write. And the test at the end of the day is that if I take one approach and I write this code and I generate a set of results, if you take your approach and write a simulation your way, at the end of the day, we should both agree on what the science is, right? We should get some information in common about, let's say, the size of a polymer chain, the relaxation times, things like that. So all that's to say there's more than one way to write this, and I'm doing it the way that I do it, the way that I understand it, but that's not to say that this is the only way that you can do it. The other thing is that I'm going to try to write this simulation in a computationally efficient way, right? So that we don't do needless calculations so that we can write this code as fast as we can. Or not as fast as we can, but so that the code performs as fast as it can. And the reason for this is shaving off milliseconds here and there can really add up, because when you run a simulation like this, you're running these loops that you'll see in the code millions and millions and millions of times. And so if you can shave off tens or hundreds of milliseconds during your loop, then you can write just a much faster code and you're not going to waste your time or waste the computer's time. I'm using C because, in my opinion, it's the fastest option out there. I think it's on par with Fortran and C++. Those are roughly, at this point, all pretty similar in terms of performance because we've had so many years to optimize their compilers and whatnot. Doing this in Python would be a bad idea, in my opinion. Python is horribly slow compared to C when you're doing something like this. That's not to say that Python is bad. Python is fantastic, depending on the task. For a simulation like this, though, it makes a lot more sense to use something like C or Fortran. Now, I know there are things like Cython out there where you can write Python code that compiles to native C and can perform, more or less the same as C code, but you're going through this extra effort to learn Cython or learn the specific syntax for that. And, you're just doing all this work. And at the end of the day, you might as well just be writing this in C or Fortran. Java's bad because similarly, Java is much slower than Fortran or C. You can do it if you want to play around with it. But if you go out on the internet and look at these simulation packages, they aren't written in Python, right? They're written in C, C++, or Fortran. Speaking of Java and C++, object-oriented programming has its place, but in my opinion, it's not for use in simulations like this. Not because of the performance hit, but because, on one hand, yes, it does make certain parts of the code easier to read and understand. It makes things more convenient. But on the other hand, it can make your code needlessly complex. And at the end of the day, we are polymer scientists. We're not computer scientists, right? We want clear code that's easy to understand, that's correct, and that gives us the science that we want, right? We don't need to go off and be all fancy about what we're doing. And then the last kind of disclaimer I'll make is the code isn't written to be rock solid, right? The code will run, the code will not crash if you do it right. But that's not to say that you can't pass some bad inputs to it that make no sense, like a negative temperature or a parameter file that maybe doesn't conform to the format that we're going to use. And you may be able to crash your code or whatever, generate results that make no sense. That's not my job, right? My job is to write a simulation that my group can use that can generate results so that we can do science. I'm not making a software package commercially. I'm not putting it out there for everyone else to use. And so I'm not so worried about, oh, is the temperature within bounds or things like that. I leave it up to the user to know what they're doing, right? So that they put in the correct parameters. So the user has to know what they're doing with the code. So here's where we are, right? The essentials of a particle-based simulation, and we're going to use DPD for this simulation. What do we need to do? What does our simulation need to do? Well, we need to read the parameters from disk, and we'll talk about what those parameters are for a DPD simulation, or at least for the DPD simulation that we're going to write here for a polymer solution. We want to set the initial configuration of the system and the initial conditions, right? What is the temperature? What are the velocities of the particles? Where are the particles, etc. We would like to be able to generate a nice movie or image of what's going on in the simulation. The data is important, but sometimes it's also helpful to be able to visualize it, right? So what you're seeing on the right-hand side here is the result of a DPD simulation using some more advanced code that I've written. And what you're looking at is just the phase separation of two fluids that are immiscible. And this movie was generated in Ovito using output from the DPD simulation. So we would like our simulation to be able to write the coordinates of our particles to disk in a certain format. We'll use the XYZ format so that we can load it into a program like Ovito or VMD and render our results, put it into a publication, put it into a PowerPoint presentation, whatever it is. As part of our simulation, we're going to have to find particles that are close enough to interact and process those interactions. And we also want to apply a periodic boundary condition. So in this image here, we're essentially simulating this infinitely large system. And the way that we do that is we reflect the system across all of these boundaries. So it's a periodic boundary condition. In 2 dimensions, that would result in mapping our simulation space to a torus. In this case, we're, I guess, mapping it to a 4-dimensional torus or something like that. We'll need to calculate the forces and solve Newton's second law. So we'll need to integrate the equations of motion to update velocities and particle positions and things like that. And we also need to calculate quantities of interest, right? We don't do science just by looking at pictures like this. We would like to get an idea of something like the radius of gyration of our polymers, so the average radius of gyration. The temperature, I have x sub p here. These are normal coordinates for analyzing the dynamics of the polymers. There's any number of things that you can calculate, and we'll do a little bit of that as part of the simulation. So in this video, we're going to restrict ourselves to reading the parameters from disk, so coming up with a format for our configuration file, setting the initial configuration of the simulation, and then writing a function to output the coordinates. And then in the next videos, we'll go through the next part of this to create a fully functional simulation. Okay, so what kind of simulation are we going to write? Well, I already said that we're going to use C because it's the fastest option out there for us. And what we're going to do is restrict ourselves to what's called a serial code. And the reason for this is it's much easier to write. So if you look here, we've got 2 options, right? One is that we could run this code, let's say, on a Unix workstation. In this case, we've got some GPUs in there and, presumably a high-powered multi-core CPU. But the thing is, with the multiple cores, the memory is shared between them. But what we're going to do is restrict ourselves to using a single CPU core. And if you want, a good exercise would be, once we write this code, you can use OpenMP to pretty easily parallelize your code so that it can simultaneously run on multiple cores and divide up the simulation problem so that it runs faster. And because this is a single workstation, the memory is shared, it's actually pretty easy to do that. And by writing a serial code, so we're not going to do the OpenMP in this video series, but by looking at a serial code, it's relatively easy to write and debug this simulation. This is in contrast to a parallel code that's written for high-performance computing environments. And I'm showing just some racks of servers here, which is pretty much what an HPC looks like these days. The memory in these things can be shared, so each server could have many cores and many CPUs, and they can share the memory. And so you could run an OpenMP code on this, but you can also divide your system up and use multiple servers. And in that case, your memory would be distributed. So in order to take advantage of distributed memory, distributed computing, you have to use message passing using, for example, the message passing interface MPI or parallel virtual machine PVM. MPI is generally use these days. PVM has kind of fallen by the wayside. Another reason we're not doing this, though, is it's a lot harder to write and debug code like this. So imagine you're trying to debug a program that's running on all of these servers at the same time with their own distinct memory, and you're trying to figure out, why is my simulation failing? And it gets really tedious. And I say this from experience. If you'd like to see a Fortran code written that does DPD in a parallel fashion, this is my open source software package that we actually use for our research. And you can see how much more complex this code is versus the serial code that we're going to write in this video series. Something that I've left out, though, is that we could also look at GPUs, right? This workstation here has some NVIDIA GPUs in there. So we could use CUDA to run this code on a GPU, or we would have to write it specifically for a GPU. And that's incredibly powerful. My group does have some code that is GPU enabled. It's really fast, but it's a little bit more complicated to write. So it lies somewhere between writing a serial code and a parallel code, in my experience. But we're not going to do GPU computing in this video series either. So let's talk about DPD. I'm going to talk about the basics, kind of the fundamentals that we need to be able to write the program. But there's a lot of details that I'm leaving out. And so I'm putting up here a really great reference from 1997 by Groot and Warren that is really a nice foundational paper about DPD. And so it goes through kind of the description of DPD, how you solve the equations of motion, some things that you have to be careful about, and then runs a DPD code and looks at some various quantities for an immiscible fluid. Really great paper. I recommend all of my students read this paper. It's really approachable. It's really great. It doesn't derive DPD, though. And so if you wanted kind of a more first principles description of DPD and where it comes from, this textbook by Frankel and Smit is fantastic. It goes over many different techniques, Monte Carlo, molecular dynamics, et cetera, et cetera. But it does have a section on DPD, and it starts from kind of the stochastic differential equations and kind of goes from there to show you how DPD emerges. But that's a little bit beyond the scope of what we're trying to do here. What we're trying to do in these videos is just start from kind of a basic description like in Groot and Warren, and then see how we would go about implementing what they describe in this paper in a very simple C code to do a simulation of a polymer. So what is it we're going to do? Well, here's what we're going to write in this video series. We're going to have a dilute solution of polymer chains. So we're going to have a couple of polymer chains in our system surrounded by solvent. And essentially what we're doing in this particle simulation is we're solving Newton's second law, right? So the time derivative of the momentum is equal to the sum of the forces. So we're going to sum up all of the forces due to interactions between pairs of particles I and j, kind of like what I'm showing here. And then we'll integrate the equations of motion to get the new velocities and the new positions. And then we'll go back and we'll solve this again, get new velocities, new positions, and do this over and over and over and track the temporal evolution of our system. So in our case, these interactions, right, that give rise to these forces between these particles are pairwise. So they're due to particles I and j. And Newton's third law says that if j applies a force on I, then I is going to apply a force that is equal in magnitude and opposite in direction. So we're going to take advantage of Newton's third law to simplify the number of calculations we need to do. So there's two sources of these interactions. One is interparticle interactions. And what I mean by that is this monomer that I'm showing in red can interact with this solvent particle J. They're separated by some distance. And so that's just, a normal interaction between two particles. In the case of a polymer chain, we have an extra interaction, though. So we still have, shown in orange here, this pairwise interaction between particles I and j, this kind of interparticle interaction. But within the polymer chain, we have an intra-chain interaction. So in this purple arrow, I'm trying to denote that there's going to be some force between these adjacent monomers that are keeping the polymer chain bound together. And so the strength of these interactions, the strength of these forces here, is really going to depend on the separation distance between the two particles. And so we're going to have a vector for every single particle in the system that denotes its coordinates, and we will compute the distance between all of the interacting pairs as we go. Okay, so in DPD, the interparticle interactions are due to three forces, and the most important one is the conservative force. This is what really gives rise to the interactions, whether something's favorable or unfavorable, et cetera, et cetera. This is really the interaction. if you're thinking about molecular dynamics, this force would be replaced with something like the Lennard-Jones potential. And so this force has a couple of terms that are important, and they're going to show up throughout DPD and throughout writing this simulation. The first one is we have got the strength of the force that's going to be denoted by this Aij term. That's just how strongly these particles are interacting with each other. But how strongly they interact with each other also depends on their separation distance. And so we've got this linear weighting term, which is weighting the magnitude of the force based on how far apart these particles are separated. And so a common choice, this isn't required, but a common choice is that we take this function to be 1 minus the separation distance. And so if particles have 0 separation distance, they actually have a finite force between them. This is unlike molecular dynamics. If you were to use the Lennard-Jones potential and the separation between two particles was 0, the force between them would shoot up to infinity. And that has all kinds of implications about how far in time you can go, and et cetera, right? So in other words, in DPD, the forces are always repulsive, and they're soft repulsive in the sense that if particles get right on top of one another, the force between them is finite, versus something like the Lennard-Jones potential, where that force diverges. Now, you probably notice in this weighting term here, there's this RC in the denominator. This is what sets the fundamental length scale in our simulation. And so we say that particles are only going to interact with each other if they're within a distance equal to RC. And we typically set RC equal to 1. So this cutoff distance is basically the range of the conservative force. Anything outside of this has no interaction with the particles inside. Well, that's not quite true. What I should say is that for a certain particle, any neighboring particles that are a distance RC away or farther will not influence or not interact with the particle in the center, right? I hope that makes sense. Okay, so that's the first force. There are other forces, though. So here's our simulation box, and what's happening is we're getting energy put into the system, so there's some kind of thermal noise, and energy is leaving the system. And so these are the dissipative and random forces. The dissipative force removes energy from the system, and the random force is a thermal noise that's kind of putting energy into the system. Okay, so you can see this minus sign here, we're kind of removing energy from the system. And the way this force looks, let's just focus on the dissipative force, is very similar to the conservative force, right? It's got a strength of the dissipation, which is given by this term gamma. It has a dissipative weighting function, omega d, which is a function of distance. And although it's not required, a common choice that we take is that we just square omega r. Okay, so we take the same term that showed up in the conservative force, we square it, and that's our dissipative weighting function. And we've got this dot product between a unit vector in the direction of particles I and j, dotted with the difference in their velocities. And you'll see this come out as we write the code. And of course, the force is directed along the shortest distance between between I and j. Similarly, there's the random force. There's a thermal noise level, so that's analogous to gamma or A in the conservative force. This theta ij term, it's just a random number, and so I put kind of the characteristics of this random number. It's got 0 mean, so it's centered about 0. It's symmetric. It has unit variance, and it's uncorrelated between different pairs and different times. That's a fancy way of saying that this number is between, let's say, minus 1/2 and plus 1/2. It's a uniform random number, so it could be anywhere on that interval. And every time we process an interaction between two particles, we have to generate a new one. That's essentially what we're doing. And so you might think if we're adding energy to the system in terms of the random force and removing energy from the system with the dissipative force, that these forces should be related to each other somehow on average so that we maintain thermal equilibrium, right? So that we maintain kBT is equal to 1 or whatever we decide to set it to. And so you would be correct if you thought that, right? So they are related. And the relation comes from the fluctuation dissipation theorem. And what we get is that sigma squared should be 2 gamma times kBT, right? So if we know what our thermal noise level is, we can compute what gamma should be. And that's what we do in practice. So those are the interparticle interactions. And so the only other interaction to describe is what happens in terms of bonding monomers together, the intrachain interaction. And so what we do is we adopt the model of Rouse. We use the Rouse chain. And this is just the bead spring model, right? So we have a bunch of monomers that I'm showing in red. We connect them to each other with springs, and the springs have a spring constant k sub h, h for harmonic. Right, so here's our harmonic potential, and the separation between adjacent monomers is Ri minus Rj, and we get a vector that looks like this with components dx, dy, dz in the x, y, and z directions. So these are just the separations between the monomers in those different directions. And this vector is something that we'll compute over and over again as we compute the interactions between pairs of particles. So I wanted to show this as an example to how we actually do this. And so we know that if we wanted to compute the force that's resulting from this potential, we take the negative gradient of it. And so the negative gradient of that potential gives us minus kh times Rij minus b. This is just Hooke's law. And the direction of the force will be along the separation Rij. So this is just a unit vector in that direction. And when we write the code, this is something that shows up and can be confusing to people when they look over the code and see something that kind of differs from, for example, what you might see in Groot and Warren. We kind of pre-compute some terms. And so if I wanted to compute the x component of this force, right? So the component of the harmonic force that's in the x direction, this is typically how I would do it in the code, and this is what you'll see. So what we do is we divide through by Rij, and so this term in the middle, which is analogous to this term here, becomes 1 minus the bond length b divided by Rij. And the reason we do that is so that dx divided by Rij magnitude gives us the unit vector in the x direction. And so I'll try to reinforce that as we get to those parts of the code. But let's stop. That's the fundamentals of DPD, at least in how we're going to apply it here. And so all we need to do is start to think about what we need for our simulation. And so this is what our simulation will look like. We're going to have a box with dimensions Lx, Ly, and Lz in the 3 directions. I'm showing them as being equal here, but they don't have to be equal, especially if you wanted to simulate something like a thin film. But for our purposes, we'll leave them to be equal here, but we'll give the ability to change them. There's going to be a certain density of particles in our system, so we're going to have 3 DPD particles. This says per RC. This should be per RC cubed, not to the minus 1. So we're going to have to input the density. We're going to have to input the size of the box in a different direction. And then some other things that show up as a result of the previous slide, right? So we need to figure out what the polymer volume fraction is going to be and what the degree of polymerization of the chains will be. We need to set the average bond length that we expect, right? So more or less like setting the statistical segment or Kuhn length. We need to set the thermal noise level, sigma, and set the value of kBt. Usually we set kBt equals to 1, and then from this we will compute gamma. I already said system dimensions. We need to set the interaction strength, so those Aij terms in the conservative force, we need to set those. We need to tell the simulation how long to run, and we need to specify the integration time step dt. Okay, so that's what will go into the simulation. And then the next thing is, okay, well, if that's what goes into the simulation, how are we going to set the initial configuration of the polymers so that we can start to simulate them? There's different ways you can do this, but what I'm going to propose and what we'll do in this video series, we'll figure out how many polymer chains are in the system and we'll put them at random places in this box. And then as we generate the polymer chains, each monomer's position will be a distance b, remember that's the bond length, away from the previous monomer, but it'll be in a random direction. So we'll use spherical coordinates to come up with this, with the positions of all the monomers. And then we should assign the velocity randomly, but with a value proportional to kBt so that we start off kind of close to the temperature that we want. We'll see that the temperature does some weird things in the initial state before it converges. So we'll kind of discuss that as we get to it. And then we'll subtract off the average velocity from the particles to eliminate any drift, right? So if you saw this movie earlier, the particles were kind of stationary, right? They were moving, but there was no net drift of these particles that would kind of look like it's flowing. So you don't have to do that. The results will be the same regardless, but we're going to subtract off the average velocity so that everything looks static and we get a really nice movie, et cetera, okay? So those are the kinds of the things that we're going to do in the video today. So let's start off first by looking at what needs to go into the simulation and coming up with the configuration file. Okay, so we have an idea of what needs to go into our simulation. So let's create our input file so we've got kind of a template for how it is that we're going to send data into our program, or what kind of data our program is going to read. So I'm going to call this parameter.configuration. And you can see I kind of already started on it. So let's just delete this and start over. Okay, so I'd like to have comments in this file, right? Because I could have a bunch of numbers that look like this. But it'd be very confusing if I went back afterwards, or a couple years later, and I wanted to figure out what was it exactly that was in this file. So what I'm going to do is we're going to have comments. So we're going to have the system size in X first, call it LX. And I'm going to assign a size of 32 for reasons. Let's just get the rest of them in here. System size in Y. Again, we're going to make this a cubic system. But remember, it doesn't have to be that way. System size in Z, 32. And what else do we need? Well, we said we needed a certain number of particles, right, that are given by the density. So let's talk about the fluid density. And in this case, it will be 3. That's a very common choice for DPD, and it has to do with the Gruton-Warren paper and similarities between water and stuff like that. Other than that, what else do we need? We need the polymer volume fraction. And we'll call it 5 poly or something like that. I don't know, 5%, whatever. We need the polymer degree of polymerization. And let's just start off with 10, although to check the code, we're going to vary that quite a bit. What else? We need the polymer bond length, and that is B. And I don't know, call it 0.7. It doesn't really matter as long as we have a good reason for what we're picking. Temperature, actually not temperature, but actually the value of kBT. Commonly set that to 1. Now, what else? Well, we need the strength of the interaction. So let's call this conservative strength. But this is going to be, let's say, particles that are the same type, right? So solvent-solvent or polymer-polymer interactions. So we'll call it AII. And a common choice, this comes from Gruton-Warren, is 25. And you can read that paper to see why we would choose 25. Conservative strength. What about particles that are different types? Well, this would be AIJ. And I'm going to set it to 25. And let's talk about what that means in terms of our simulation. All forces are repulsive in DPD. And so if we set this to be the same, it turns out that this mimics a good solvent. Not a theta solvent, but this is actually a good solvent in DPD if you set these to be the same strength. If you were to set this to be something like 35, then what this means is that polymer-solvent interactions would be stronger than polymer-polymer interactions, or solvent-solvent interactions. And what you would get is phase separation. So we don't want that. We want our polymer to be well dissolved. So we'll set those to be the same. But after we write this code, I encourage you to set that to 35 or something like that and see what happens to your system. Okay, we got the conservative strength, harmonic strength, right? What is the spring constant in that harmonic potential? I'm going to set it to something like 50. This is just a value that I know keeps the chain together. You could experiment with other values if you wanted. Thermal noise level, sigma. Common choice is 3. Doesn't have to be 3, but that's a very common choice. Again, that goes back to Gruton-Warren. And it's a good idea to do, right, to set it to equal 3, because if you want to compare your results to other results in the literature, a lot of people use 3. And so if you use these similar values, it helps you to benchmark or validate your code against other people's, right, other research that's been done. What else? We need the integration time step. I'm going to set this to 0.01. You can experiment with this. If you make it too large, your simulation could explode, literally, right? It means you're calculating huge jumps in the particle positions, and you can get things that leave the system and then everything breaks. And this is an example of, I'm not checking this. I'm trusting the user to know what they're doing. And so I know this value works. I'm trusting that you will figure out what works. You can go a little bit higher, but this works. The higher you go, either your simulation blows up, you can't stabilize the temperature, you get larger errors, things like that. So this is a good value, but you can use larger or smaller values. What else? How long the simulation runs. So let's say We need to equilibrate the system, so equilibration time steps. This is, let's say, time equilibrate. And I don't know, 10,000 will be enough for us, but there are metrics by which we can evaluate whether or not the system is equilibrated. And then production time steps. This is the number of time steps that the simulation will run to generate the data that you're interested in. So let's say 1,000,000, right? And so there's our configuration file. So now all we need to do is write C code to read this and get these parameters and get them into the code so that we can start to do our simulation. Let's start with our code. Before we do that though, let me make a make file. Very, very, very basic make file, just so that it's just faster for us to compile our code. And so we'll just type make in this directory and it'll compile our code for us. So we'll use GCC. We'll optimize it as much as we can. We'll output a file called DPD. That'll be our executable. dpd.c will be our source file, and then we need to link the math libraries. And at the same time, I'm going to put debug in here. I already know that this code works, but just in case we wanted to debug this with GDB or something like that, I'm going to give us the option to compile it for debugging and also to clean up our directory. And so we'll remove DPD, any object files which we shouldn't have, any data files, and any XYZ files, just to make our lives easier. And I think that should do it. So if I type make, well, I've got all kinds of errors right now, and I'll show you why. Okay, so let's edit our DPD code. So what I've done is I've already put some things in here, and what I've put in here are a random number generator, so ran3.c. I'll show you that in a second. These are some of the variables that go along with it, the most important of which is this random seed that we'll talk about. If we want to do a DPD simulation, you've already seen that it depends on random numbers quite a bit, whether for generating a random initial configuration or for processing or computing the random force. So we need random numbers, but we don't just need any random number. We need a uniform random number, and we also need a random number generator, I guess more accurately, a pseudo-random number generator that has a very long period. And what that means is that if I'm generating billions and billions of random numbers, the sequence will not repeat itself for a given initial seed. Okay, so we don't want a random number generator to repeat itself. What this means is that we typically use high quality random number generators. Ran3 is a very simple one that was taken from numerical recipes. Fortran NC versions exist. And so that's what I've done here. And if we look at Ran3, here's the Ran3 function that comes straight from numerical recipes in C, and this is what we'll use. So here's how the random number is generated. To be honest with you, I don't really understand, and I don't really care because I'm not a computer scientist. I just know that this works, right? Okay. So that's what's in dpd.c right now. So what we need to do is we need to start constructing our code. And so we'll have pi here to good amount of digits. We've got our main function, which is the entry point for the program, command line arguments if we wanted, which we won't use. And here's the random number generator. So let's start putting in the things that we need. We're going to need standard IO for printing to the screen and, you know, stuff like that. We need standard library for opening files and doing stuff like that. Other things that we need string.h, and that's going to come into play for initializing our arrays using some cool memory functions, and also for reading our text file. We need also time.h. This is going to allow us to just automatically set our random seed so that we don't have to do it in the configuration file. So it'll just randomly set whatever the seed is. And so every time we execute the program, we'll get a different sequence of random numbers. And of course, we're doing science, so we'd better have math.h. Okay, so those are the system headers that we will use. Here's our random number generator. The next thing I'm going to do is put in our global variables. And here's where I come back to my little point about I'm not a computer scientist, I'm not a software developer. there's time for global variables and there's times where you don't use global variables. I could put all of these inside the main function. I could pass them around, but I don't want to, right? I'm just trying to write a simulation. I'm not trying to get an A in some computer science project. So all of the variables that describe our simulation, I'm going to make global so that in any function or subroutine that I'm in, I can refer to them, right? I don't have to pass pointers around and do all this crap. This is what I'm going to do. If you want to put them inside main and not use global variables, be my guest. I'm using global variables. All right. So what do we need? Well, the first thing we need is we need the coordinates of our particles. So here's the x, y, and z coordinates. Notice that I'm declaring them this way. This is because they're pointers, and I'm going to allocate them dynamically based on the size of the system so that I don't have fixed length arrays and so that I only use the memory that I actually need. So these are going to be the coordinates with the periodic boundary condition. And something that I didn't really touch on in the introduction is that we've got some other things as well too. We have coordinates that do not have the periodic boundary condition. And the reason for this is that this makes calculating the interaction between adjacent monomers much easier because we don't want to have to deal with the fact that a monomer could be on one extreme end of the system and another could be on the other extreme end of the system. So they're separated by a big distance, but they're actually just looking that way because they've been wrapped around because of the periodic boundary condition. So we could do it that way and we could figure out what their minimum distance is, or we can just have a separate set of coordinates that aren't subject to the periodic boundary condition. And that's how I'm going to do it. Well, because it's easier and memory is cheap. Okay. All right. What else do we need? We need the velocity, the x, the y, and the z directions. Some things that I didn't talk about, we'll talk about it when we talk about the velocity Verlet algorithm, is we need to store the velocities from previous time steps. And so we'll come back to why these are here in a second, in a little bit, but we need them, right? So we need to store previous velocities. And I'm sorry, I'm a little anal about this. I have to have my equal signs and comments line up. It just bothers me if they're not. Okay, so these are velocities, previous time step. What else do we need? We need our forces. Y, F, Z. These are our forces. Current time step, and of course the velocities, current time step. We also need to store our forces from the previous time step. And this is, again, because of the velocity Verlet algorithm, and you'll see when we get to them why we do this, and I'll explain why when we get there. Okay, so we've got those. What else do we need to know? Well, we need to know what type of particle we have, whether it's a solvent particle or whether it's a monomer. So this is the particle type or species. What else? Okay, so done with the pointers. Now we need to know the dimensions of the system. So this is more or less mirroring the configuration file at this point. We need the fluid density. Got that. We need the volume fraction of polymer. Very good. We need the degree of polymerization of the polymer. We need the bond length, or the equilibrium bond length, let's say. I'm going to put this here. We're going to actually keep track of what the actual bond length is in our system, because we're going to find that it's not going to be equal to B exactly. It's going to have some average value. So this is the average bond length that we calculate from the simulation. We need temperature, or more accurately, this is the specified value of kBT, which will be equal to 1. Why not? We can calculate the potential energy. because we can calculate the kinetic energy. In fact, we can use the kinetic energy in the equipartition theorem to calculate what the value of kBt actually is in our system. And this is one way that we can guarantee, or maybe not guarantee, but have some insight as to whether or not our simulation is 1, behaving, and 2, has reached equilibrium. It's not the only one. We also need the interaction strengths. So here's conservative interaction strength for like particles. And this is the conservative interaction strength unlike particles, right? So like monomer solvent interactions. We need sigma and we need gamma. The gamma keyword is already taken by the gamma function. So we'll use gamma 1 to be the dissipative strength. So this is random and dissipative strengths. We need the strength of the harmonic potential, so the bond spring constant. We need the integration time step. What else? We need the number of equilibration steps that we'll do. Of course, we need the number of production time steps that we'll do. Am I forgetting anything? Oh, of course, we need the current time. And the reason I'm making this global, this will be in a for loop in main, but the reason I'm making it global is so that we can see in different functions what the current time of the simulation is, just to help us, for example, with output to files and things like that. So this is the current time step. How about the number of particles that we simulate? So this is the total number of DPD particles in simulation. And then finally, the number of polymers that are in the simulation. All right, so that's pretty good. Okay, so where are we? These are all the variables that we need for our simulation. Here's the main function. The only other thing that we need are function prototypes. So I'm going to put the functions underneath main, so we need function prototypes. And so let's see here. Which ones are we going to do today? In this video, what we're going to do is say void initialize system. So that will create the initial random configuration, set the velocities, etc., etc. We need to read the parameters from file, and we will specify the file name. And the last thing we'll do in this video is we need to write the coordinates to disk. And so we'll write an XYZ file. We'll pass it to it the file name, and we'll pass to it whether or not we want to append. Okay, and so that's pretty much all we've got now. We have the full thing going. So what we need to do first, before we can really do anything, is we need to read the parameters from the file. So let's create that function down here. Read parameters. Again, we pass the file name. This function returns nothing. So we're going to do two things. And notice that when we created our configuration file to begin with, one of the things that we did is we had comments in there. So first we need to be able to open our parameter file. And I'm going to put this thing in here. Again, this is an example of Mike Hoare is not a computer scientist, so this is how I'm going to do it. There may be more efficient ways to handle those comments, but this is how I'm going to do it. Okay. So again, we've passed the file name, so let's just open it. The param file will be what happens when we open file name, and we're going to open it for read access. And I don't do a lot of checks in the code because, again, I'm trusting that the user knows what they're doing. I'm not making some super robust commercial product here. Largely, this research code is just used internal to my group. But, you know, maybe we'll just make sure that the file exists and we're not trying to open something that doesn't exist. So if that handle is null, then we'll say the parameter file is not found. And we will exit the -1. And that's that. Okay, so that's us checking to make sure that the file's there. And now we just need to go line by line and read in everything. So what we're going to do is we're going to read in the comment line. So we'll get from the file, put it in junk, maximum of 256 characters, and we'll get that from the param file. Okay, so now we're on the next line, and we need to read in the value that follows. And if you remember from our configuration file, the next one that follows is, first of all, a double precision float. I should have said this earlier. We use double precisions. We really need that precision. All right, so we don't use floats. We use doubles in our simulation. So the first one was the system size in the x direction. Okay, so now we've read that value. So all we need to do now, and I'm going to speed it up to spare you the agony of watching me do this bit by bit, is we need to copy these two lines and then paste them and make adjustments perhaps to the type for everything that we're going to input into the simulation. All right, so I'm going to do that very quickly, and then we'll come back and we'll talk about what we do next. At this point, we've read everything in from the file. And so if you remember, gamma is defined in terms of sigma because of the fluctuation dissipation theorem. So now we need to define gamma from our value of sigma. And we're actually going to rescale sigma in a, might seem like a weird way, and I'll explain why we're going to do that. But first of all, gamma 1, if you remember, should be sigma squared divided by 2 times kbt, and then the variable names that we're using here, kbt is just equal to capital T. And then the rescaling of sigma, we will have sigma multiplied by the square root of 3 divided by dt. The reason that we're doing that is, if you remember the equations for the three forces in DPD, the random force has delta t to the -1/2 power, whereas everything else does not have t in it. So by pre-computing sigma this way, it means that we can treat sigma on the same basis as the dissipative and conservative force for when we use the velocity Verlet algorithm. So this is just saving us some notation and some trouble ahead of time. And with that, we've read everything in. The other things that we can do for our code is, why don't we go ahead and set the random seed for ran3. So set seed value for ran3. And so that is iSeed. And what ran3 expects is that the random seed should be a large negative integer. So we'll set this to -time0 so that every time we execute the program, the seed will be different and we'll get a different series of random numbers. So the only other kind of lengthy thing that we have to do in this video is we need to initialize our system, and we need to do it according to what we said we would do earlier on, right? We're going to put all of the particles in random positions, we're going to assign random velocities, and we're going to subtract off the net velocity from everybody so that there's no drift. And that should do it. So let's just put return here, and let's get to it. So let's see what first. Let's declare some of the variables that we're going to use. So we need some integers, I, J, K. And what else? We also need 2 angles. We need phi and theta from spherical coordinates. So we need, let's see, phi and theta, so the polar and azimuthal angles. And probably some other things that are escaping me at the moment, but let's just get started with initializing the system. So the first thing is we need to figure out how many DPD particles are going to be in the system. So let's figure out how many DPD particles are in the system. And we can do that based on the density, right? We said that there should be 3 DPD particles per RC cubed. So n DPD should be an integer, and it will be the density times the volume of the system. So Lx times Ly times Lz. And so let's calculate the number of polymers in the system, right? So NDPD includes all monomers and all solvent particles. let's figure out the number of polymer chains that would be in the system. So n poly is also an integer, and it will be the volume fraction of polymer times n DPD. So that's the number of monomers that would be in the system. And so if we divide by the degree of polymerization of a polymer chain, that gives us the number of polymer chains. And maybe we can write some output to the screen to let the user know what has happened. So we'll say something like, there are so many DPD particles and so many polymers with chain length of whatever. New line, and let's see, that would be n DPD, n poly, and n. All right, so now we know how many DPD particles we've got, how many polymers we have. So now we should allocate memory for our X, Y, Z, etc. arrays. Right, so we declared those things as pointers, so let's start to allocate memory for these. So for example, X is going to be, we said it was a double, and so we allocate memory, and we need n DPD because that's how many particles will have an X coordinate. And we need to multiply that by the size of double so that we know how many bytes to allocate. And so we would do this with also Y and Z. Right, so now we've allocated X, Y, and Z. What else? Well, we've got the arrays that are not subject to the periodic boundary condition. So Rx we can define in Ry and Rz. And what else? Well, we've got velocity in the X, Y, and Z direction. Well, we've got the velocities from the previous time step also, right? So we've got Vxp, and again, I have to have my equal signs lining up or it drives me crazy. So now we've got the positions, the velocities, we need the forces. So Fx is going to be the same thing. So double star malloc n DPD times size of double. Fy, Fz. Got it. We also have to store the forces from the previous time step, right? So we've got those allocated. And the only other thing, and this is going to drive me crazy because it's going to mess up my equal signs probably, is, one second, makes the code look nice, but it's a lot of time pressing the space bar. Okay, and we need to know the particle type. And so this is not a double, this is an integer, but we'll have still n DPD particles, but now this will be the size of an integer. And now we've allocated all of our memory. Now, we have to be really careful, right? You can get into trouble with C and C++ allocating memory. The way this is done, we don't have to worry about memory leaks and using up all the memory on our system just because of the way this code is structured. So, for example, we would only call initialize system once, but you can really get into trouble with malloc. Good practice, as soon as you allocate something, you should free it. So we're going to go up to main. Once our simulation is done, we're going to free all the memory that we've allocated. So we're going to free X, free Y, free Z, free Rx, free Ry, etc., etc., etc. So let me just type this out really quickly, and I'll meet you on the other side. All right, so just a few things left to set the initial configuration. One thing I remembered, those variables I was missing, I need the total, or what will eventually be the average velocities in the X, Y, and Z direction, so we can subtract them off. All right, so let's start to construct the initial configuration of our system. Let's put the polymers in first. Okay. So what are we going to do? Well, let's first of all initialize our total velocities so that we can calculate the average to subtract off later. Because what we're going to do is we're going to simultaneously come up with random coordinates, random velocities, and assign the particle type. So it would make sense to compute the average velocity as we're adding more and more particles to our system and defining the velocities, right? And let's also use this as an index to keep track of where we are in our array. So what we're going to do is, let's say we look at all of the polymers in our system in a for loop. If you haven't written a simulation like this before, for loops are like the bread and butter of computer simulations. Anyway, so we're going to do that first. And so what we're going to do is let's first of all assign a random position in the system. Okay, so this is going to be like the first monomer in the polymer chain. So we'd say something like x of k is going to be equal to ran3. It needs the address of the random seed because of how ran3 works. And it'll be some random position in Lx. Because ran3 goes from 0 to 1, then that means that the position of the monomer could be anywhere from x equals 0 to x equals Lx. So that makes sense. Same thing here. So y will be some random position along the y direction, and same for z. We will worry about the coordinates that don't have the periodic boundary condition after we do this. Okay, so let's hold off on that, but we've got the position. Okay, so the first monomer is now in a random position in the system. Now assign a velocity to this particle. Now imagine we've got our particle, we need to assign a velocity. So the velocity is going to have a random direction to it, but the magnitude should be related to kBt, right? Because of the equipartition theorem. So let's do it this way. Let's say that theta, and again, we'll use the physics convention where theta is the angle that our vector makes with the z-axis. So that means that theta goes from 0 to pi radians. Theta will be a random number between 0 and pi. And phi would be the angle in the xy plane. So again, using the physics convention, so this would be a random number between 0 and 2 pi. And now we can assign our velocity. So the velocity in the x direction will be, let's say, the square root of the temperature, or square root of kBt, times cosine of phi times sine of theta, if I remember correctly. In the y direction, we'll do the same thing. Sine of phi times sine of theta. And then in the z direction, this will be square root of t times cosine theta. Okay, so those are our velocities. And now let's just add to our total velocity so that, again, at the end of this, at the end of placing our particles, we can compute the average. And so the velocity in the x direction will be that plus the velocity that we just assigned. Same for y. And same for z. You know, I was thinking about the fact that I like my equal signs to line up. One of the benefits to that is it makes it really easy to spot typos and mistakes as you're writing your code. So that's one reason I would do it. Okay, assign the position, assign the velocity, now assign the particle type. And let's say that, first of all, remember this is an integer. So let's say that particles that are monomers will have a particle type of 1. And we'll see when we compute forces how we take that into account to handle things. But for now, let's just make all monomers particle type 1. And now we're going to next add another particle to the system. So let's increment that integer k. All right. Okay, so we got the first monomer in the chain. So now we need a second for loop. So for j equals 1, and j should be less than n. Right, so we're going to add the rest of the chain. And essentially what we're going to do is we're going to repeat everything we did up here. So I'm just going to copy and paste this. This is what, 4 or 5 lines, 8, 11, 14, 15, 16, 17, 18, 19 lines of code or something like that. So we'll copy those, put them in here. So we're going to do exactly the same thing. Except we're going to assign the positions a little bit differently, but we'll assign the velocity exactly the same way as we did for that first monomer. And we're still going to add to our totals like before. The particle will still be type 1. We still will need to increment that integer. And is my loop closed? Yes, my loop is closed. Awesome. Okay, so the particle here, this is going to be a little bit different right here, right? Because we don't want to just put the monomer anywhere in the system. The monomer should be a bond length away from the previous monomer in the chain. So maybe I shouldn't have copied and pasted that, but whatever. So we're going to, again, do this in spherical coordinates because of the symmetry. So theta will be still a random number between 0 and pi. Phi will still be a random number between 0 and 2 pi. And we're going to say that the position of this monomer will be the position of the previous monomer plus the square root of b. That's b is the magnitude of the vector, right? So square root will be, well, it is what it is, right? It's just vector math. Square root of b times cosine phi times sine of theta. So the y-coordinate of this monomer will be the y-coordinate of the previous monomer plus square root of the bond length times sine of phi times sine of theta. And the z-coordinate will be the z-coordinate of the previous monomer, same thing, right? Cosine of theta. So now we've got all the polymer chains generated. So now we just need to generate or replace the solvent particles into the system. And this is much easier, right? Because we don't have to worry about the connectivity of the solvent particles because, well, they're not connected to each other. They're just simple beads. So this is actually a pretty quick thing to write here. So all we need to do is another for loop. So for I is equal to k, right? So that's why we had k. It allowed us to identify the correct index for the particle that we're placing. But now that we've placed all these, now we can just jump into the loop and pick up where we left off and just make sure that we stay less than the number of DPD particles in the system. And we won't have nested loops in this case. And so again, random position. So x of k will be equal to rand3 times lx. yk, same thing. And same thing here. And we need to place, or we need to set the velocities. I'm going to be lazy. I'm just going to copy this, right? So we've got what? 9 lines. So down here, we'll put those 9 lines assigning the velocity. Boom. We've got a random velocity. And what else? We need to set the particle type. And now this is solvent. I'm going to set the particle type equal to -1. This makes it really easy to determine whether or not you have 2 like particles interacting or 2 unlike particles interacting, like monomer solvent. So that works, but you know, as long as you're using prime numbers, you can do whatever. And of course, we need to increment that. We could have used I guess, instead of k in this loop, but I don't think it really matters. All right, just a couple things left. We need to set our non-periodic boundary condition arrays, and this is why I love C, because this is a lot harder in Fortran 77. So set the non-periodic boundary condition arrays. Simple, right? We'll just copy to Rx the array X. We've got the size n DPD times size of double. So we've just copied that array. Maybe newer versions of Fortran have this feature, but I don't know. But this makes life really easy when you're using C. You can also initialize arrays in a similar way, a lot easier. All right, so we did that. Finally, subtract off the average velocity to eliminate any drift. So the average velocity in the x direction will be whatever it is divided by n DPD. Let's say double DPD. Same in the y direction. So we're dividing by n DPD to get our average. I wish Fortran had this syntax. It's so much quicker. Okay, and so now we just need to loop through all of our particles. And we'll say what? Vx I is equal to Vxi minus the average velocity. Same here. And that's it, right? So that's our initial configuration. So the very last thing that we need to do is we just need to write the function that will output our coordinates to disk, because otherwise where we are right now, we haven't really done a lot that's useful, right? We haven't simulated anything. We've just placed all of our particles in the system. So let's at least be able to write them to disk. And so I like to keep my functions in alphabetical order. Again, I'm kind of little OCD about doing that, but it helps me keep my code organized. And so again, XYZ, we pass the file name and an integer that specifies whether or not we append to the file. So if we append, we can make movies in VMD and Ovito. If we don't append, then we just get whatever frame we've output, okay? All right, so what do we need here? We need the output file and an integer to iterate on. And so, I don't know, let's tell the user something. We'll say we're writing coordinates to whatever file name we have. Okay, so we'll display that to the user. This is helpful even if you run this on a cluster, right? If you go back to the logs to see what your code actually did. And we'll say if append is true, then we will open our file and append. Otherwise, we will just write to it and have the most recent frame. And so now what I'm about to put in is specific to the XYZ file format. You can go to Wikipedia or any number of sources and get an idea of what the file format is. But basically the first line should be the number of particles in your system. The next line is a comment. And then after that, there's a very specific way that you write your coordinates. And so let's say first we need to output the number of particles we're going to put in there. Now, if we wrote both the polymer and the solvent to the file, it could be very difficult to see what's going on. So let's only write the polymer to disk, okay? So the number of particles would be the number of polymers. So let's get this right. Would be the number of polymers multiplied by their degree of polymerization. And here we could say, we could put a comment in. This is a snapshot from time t equals whatever, and we could put the actual time step in there. Okay, so that's why I made it the global variable. Of course, you could pass it to the function, but whatever. And then the last little bit for I equals 0, I is less than n poly times n increment. And we will say f print f, and here's where the format of the line in the XYZ file format kind of matters. You need to tell it what type of atom it is. I'm just going to say carbon, knock yourself out, put whatever you want in there. I'm going to truncate the coordinates a little bit so that the file looks a little neater if we were to look at it in a text editor, but again, you knock yourself out and do it however you want. You all are, after all, the whatever. I was trying to come up with something clever. You're the boss though, right? Okay, so X, Y, come on, and Z. Close that loop. Okay, so that writes out all the coordinates, and then we will close the output file and return nothing. And that's it. Okay, so in the last hour or so, we've talked about what we do in DPD, kind of the fundamentals of DPD. We set up our code, right? So we've got all the variables that we need to do a simulation. We've initialized the system with parameters that we read from file, and we gave ourselves a way to write out the coordinates so that we can look at them in a program like Ovito. And maybe in a second, I'll do that with this code just so we can see what we've generated. But as it's written, this code isn't going to do anything, right? This code is going to print a blank line, set the random seed, and free memory that hasn't been allocated, which is going to make the system really unhappy. So let's do some things. Let's read the parameters from disk. So we will call read parameters, and remember we called our configuration file param.config. Okay, so now we've got everything in there. Next thing we need to do is create a random configuration of particles. So we will initialize system. And then for the hell of it, let's write out the polymer coordinates to initial config.xyz. So we will say write xyz, and we will say what? Initial config, and append no. So if there's anything there from a previous run, we will not do it, and then that's it. Maybe we'll do some more cosmetic stuff. And that's it. So that's the skeleton of our simulation. When we come back in the next video here, we're going to calculate forces next. And then what we're going to do is move particles, update velocities with velocity algorithm, calculate some stuff like RG, temperature, momentum, and then end. So that's what we have going on. So let's try to compile this code, and let's see, first of all, if it compiles. Secondly, if it runs. We'll take a look at initial config.xyz to make sure it works. And then maybe we'll load it up into Ovito and see what it looks like. Okay, moment of truth. Let's take a look. What do we have in here? We've got our make file. We've got our DPD code we just wrote, random number generator, and our configuration file. So let's remind ourselves of what we've got. 32 by 32 by 32 system, 5 volume percent polymer, degree of polymerization 10. Here's all the stuff, the interactions we're not even going to use yet. And let's try it. So, hey, it compiles without any errors. That doesn't usually happen. Usually some mistake, like I forgot a semicolon or something. And let's run it and see if our code works. All right. So it looks like it. This is how many DPD particles correspond to that density for a system of 32 cubed. 5 volume percent corresponds to 491 polymers in there, each with a chain length of 10. And you can see it wrote the coordinates to this file. And so let's take a look. Here's our XYZ file. So again, these are the number of particles. So we had 491 polymers times the degree of polymerization, which was 10. We've got 4,900 particles in here. Here's my comment, snapshot from time t equals 0. You can see each line is just atom type, and they're all the same because it's all the polymer. So I said carbon, the X, the Y, and the Z coordinates. And so here they are for everybody in blocks of 10. So that looks good. So let's just open it up in Ovito and see what this looks like. So here we are in Ovito. I've loaded in the XYZ file, and you can see the excerpt here, right? We've got, again, 4,910 particles, snapshot from time t equals 0. And here's the first couple lines. So let's import it. And we've got this mess. It's kind of hard to see what's going on, right? Imagine what it would look like if we had the solvent in here. So I'm just going to shrink these particles a little bit so we can kind of see what's going on. Maybe make them a little larger. So this is the initial configuration that we've generated. You can see the groups of polymer chains, right? So here's maybe one polymer. Here's another polymer, but it gets kind of hard to keep them separate. And then, of course, mixed in with all of these is, solvent particles and stuff like that. So maybe we can render this, show it to our friends, be like, hey, look, I wrote the beginnings of a DPD simulation. So here it is. We could put this in a paper if we wanted, although we probably wouldn't. With Ovito Pro, you can make much better images, or with a VMD, you can make much better images that would look good in a publication, but so far it looks like everything's good. So I hope that was useful for you, and I hope you join me in the next couple of videos as we fill in the gaps in our simulation. And within, probably 2 or 3 more videos, we'll be done with this code, and we'll have a complete DPD simulation, and then we'll look at whether or not it makes sense based on what we know about polymer physics. See you then.